Welcome. So, we are discussing about the steepest descent algorithm, where we have seen that solving a problem a x is equal to b is equivalent to find out minima of the functional j x, where j x is defined as x transpose a x minus x transpose b. And in order to propose an iterative method for solving or for finding the minima of j x, we discussed about the gradient search algorithm, that choose any value x 0, find j x 0 there, and then find out the gradient of j and move along minus gradient of j, and move up to a certain distance where this along which j reduces on that particular line, and this distance is measured by parameter alpha. We have discussed about how to find out alpha till which j reduces along that line, and then when you see that j has reached a local minima along that particular line, change the direction and go to the take another direction. So, roughly it is this particular method that start with one particular x 0, move along one direction, and then see that this is a local minima of j. From here you take another direction, and that is how you approach the global minima, and this is the parameter alpha, that distance should be covered in particular one particular search direction, so that the search is optimum, and in least number of steps we reach the local minima. Now, we thought about taking this into a solver and writing an proposing an algorithm for iteratively solving x is equal to b or finding j minima using this, which is called the steepest descent algorithm. Let k be the kth iteration value, and the error is defined as dk is x k minus x star, where x star is the solution of x star is equal to b. X star is the where we have the solution x star is equal to b, that is the location where j is minima. So, this let x star be the point where j is minimal, and dk is the error, that means we considered a guess value x k or kth iteration value x k, dk is the error which is x k minus x star. The residual is defined as b minus a x k. If x k is equal to x star, we reach the right value, b minus a x is equal to 0. So, residual is 0 till it is not reached, this is a non-zero value, and we define residual as b minus a x k, or this is equal to b into a into d k. Why? Because b minus a x k is equal to b minus a x k minus b minus a x star, because this is 0. So, this is residual is dk is equal to So, there is a small sign convention issue. R k is b minus a x k, and this is so okay. So, let us define this is equal to x star minus x k, this is minus d k, then it should come out. So, this is minus of a into x k minus x star, which is a into d k. So, let us define minus d k is x k minus x star. So, now new iteration guess will be updated as x k plus 1 is equal to x k plus alpha k into minus gradient of j x is equal to x k. So, it started with a value of x k, and we will update it to the new iteration x k plus 1, and this is how, because we are also, when we are thinking of solving x is equal to b, we are also trying to find out the minima of j. So, you should go along minus grad j x k, and we have found out there is a parameter alpha k by which we should go in that direction. So, I have j x is equal to half of x transpose a x minus b, grad j is equal to A x minus b, as A is a symmetric matrix. X k plus 1 is equal to alpha k into minus grad j of x is equal to x k, which is evaluated at x k, we have seen that earlier, and minus grad j is b grad j is A x minus b. So, minus grad j is A x minus b, therefore, minus grad j is b minus A x. So, x k plus 1 into alpha k into b minus A x k, and we have defined b minus A x k as r k. So, this is x k plus 1 is equal to x k into x k plus 1 is equal to x k plus alpha k r k. R k is the same vector as the vector direction, as the same vector in the direction v. R k and v are same, right, because we have written earlier v is equal to minus grad j. Now, we can see that v is same as r k. So, I have seen that alpha is equal to v, if v is minus grad j, now we have seen that minus grad j is r k. So, r k and v are same. Alpha is equal to v transpose b minus A x k, v transpose A v. So, we will get alpha is equal to r k transpose, r k and v are same, b minus A x k by r k transpose A r k, which is r k transpose r k into r k transpose A r k. And there is one observation, which is r k and r k plus 1 are orthogonal. Why? Because grad j is the direction in which j reduces fastest. Grad j is perpendicular to the j contour where it was evaluated. Now, we move till j is minima or grad j, this is tangential to j contour to tangential to j contour at x k plus 1, this is x k plus 1. The new direction is minus gradient of j x at x k plus 1 is perpendicular to the tangent. So, this grad j x k and grad j x k plus 1 must be perpendicular to each other. Therefore, r k and r k plus 1 are orthogonal vectors. So, nevertheless, we have found out that for one particular iteration how to find out alpha k. So, the steepest descent method will be start with one guess value x 0 and then do an iteration k is equal to 0, 1, 2 until it converges. Compute r k is equal to b minus A x k, compute alpha k, which is r k transpose r k by r k transpose A r k, update x k plus 1 is equal to x k plus alpha k r k, and check if r k is less than an epsilon is a small value. If the residual b minus a, I have to see whether b minus a x is equal to 0. If b minus a x is a very small value, then sorry, if not a very small value, if it is a very small value, then it is iterated. If it is not a very small value, then set k is equal to k plus 1 and go to the 2 and do the try for the convergence of the iterations. If else, if this value is very small, r k is a very small number, then you say that iterations are converged and you have reached the right solution. So, this is roughly the steepest descent algorithm what we discussed here, and for a symmetric positive definite matrix we can utilize this irrespective of the way it has been represented as a diagonal dominant matrix or not. Only we have to see that this matrix is symmetric as well as positive definite, and we can utilize this method. And this is in general a faster method for symmetric positive definite matrices. This is a faster method than Gauss-Seidel SOR or Jacobi method. However, when we look into this method, we see that if we try to think do a computer program here, there are two matrix vector multiplication here, A into x and A into r. So, if I have a million by 10 to the power 6 by 10 to the power 6 matrix, each of these steps needs multiplication with each element of the matrix with the vector, each component of the vector. So, in a sense 10 to the power 6 into 10 to the power 6 multiplications are needed. Each row needs 10 to the power 6 multiplications and there are 10 to the power 6 rows. So, this particular method needs in Gauss seidel in each iteration we only have to do one Ax multiplication, because xi is equal to b minus sum of ai ij x j at the older value except the diagonal term. So, there is only one matrix vector multiplication, there are two matrix vector multiplications. If I try to do a computer program, write a computer program out of it, though the number of steps will be less than Gauss seidel, however, the calculations will be way high for large matrices, because they are doing in each iteration the calculations will be way high for the large matrices, because they are doing lot of the Gauss seidel is doing only once matrix vector multiplication, whereas the steepest descent will do it twice. So, you need to modify this algorithm. So, you have seen that there are two matrix vector multiplications and two vector product. Vector is R k transpose R k and R k transpose A R k, which is another again another vector, is the vector product. However, they are less time consuming, because if there are 10 to the power 6 rows, then only 10 to the power 6 operations are there. However, matrix vector is 10 to the power 6 into 10 to the power 6, 10 to the power 12 operations are there, is a very computationally costly operation. If there is a matrix vector multiplication, it is done twice. So, we have to see how can we reduce the cost of the computation or number of operations, or can we improve the algorithm little bit better, so that we can at least avoid one matrix vector multiplication here. So, that for million by million matrix 10 to the power 12 floating point operations are saved if I can do one matrix vector multiplications here. So, you need to look into some modifications, some possible modifications into the steepest descent method before we propose an algorithm for computer programs. So, the idea is again if I go back to the previous slide, that why I need two matrix vector multiplication, one is needed to find alpha, another is needed to find r, and every time we need to do one matrix vector multiplication to find the updated value of r. R k is equal to b minus a x k. Once we update x, we need to do a matrix vector multiplication here. So, that is actually replaced here. Updating r k plus 1 is equal to b minus a x k plus 1, which is b minus a x k b alpha k r k, which is b minus a x k alpha k a r k, that is r k minus alpha k a r k. And if I go back to the previous slide, a r k is needed also for computing of alpha k plus 1. So, if r k plus 1 can be computed using a r k, then this is the only matrix vector multiplication which is common both to calculation of r k plus 1 as well as to the computation of alpha k. And in that light we will try to modify it. We will see that this is also needed for computing alpha k. So, while computing alpha k, we will store a r k and you will utilize this for updating r k plus 1. The final steepest descent algorithm will be start with a guess value of x is equal to x 0, compute b minus x and r is equal to b minus x, and define a new variable p which is AR, p will be utilized later, and until convergence, that means convergence means that until r is less than epsilon, epsilon is a very small number, do compute alpha which is r transpose r into r transpose p. So, alpha is equal to r transpose r transpose AR, and now AR has been substituted by p. Update x is equal to, this is because the same variable x which is overwritten as x is equal to x plus alpha, that is why we are writing x arrow is equal to x plus alpha r. This is a way to write something which is getting overwritten. Update x is equal to x as x plus alpha r, update r. So, r k plus 1 is equal to r k minus alpha k a r evaluated at kth level. So, this is r k minus alpha k p k p k. So, update r is equal to r minus alpha p, compute p is equal to a r, and then if the convergence is not done, undo means you again come back here and further with this the new value of p compute alpha, update x, update r, and repeat this loop until you see that r is less than, mod r is less than epsilon, or convergence has been achieved. So, this is the steepest descent method algorithm, and this is applicable only for asymmetric what happens if A is not symmetric positive definite? Then the problem we are solving, in this problem what we are solving here is not finding x is equal to b, is solving what j is minima. The problem we are solving is not j is minima, is not now solving x is equal to b, something different. Is if it is not symmetric, we are solving half of a plus a transpose x is equal to b, a different problem. So, we are trying to find out minimum of something which is not x is solving x is equal to b. However, where convergence is based on mod r is less than epsilon. So, either it will not converge, but if it converges, then it will take us to the same solution, that mod r is less than epsilon. So, x is equal to b. So, in case the matrix is not symmetric, or matrix is little not, the asymmetricity is not very high, I k is probably a k I plus a small number. In that case, it still converges, but it takes lot many iterations, it does not take less number of iterations, because we are not using the right solution algorithm for that cases. However, if only if the matrix is symmetric positive definite, then using this method is advantageous in terms that the formulation is complicated one, program is also probably little complicated than the Gauss-Seidel method. However, this is advantageous because it saves times, the number of steps are small, number of iterations are small, calculations in each iteration is compared to Gauss-Seidel. So, overall computational cost is less if we apply this method. Only if the matrix is symmetric positive definite, then application of this method is worthwhile. Otherwise, it might give us the right result, because we are looking for this criteria that mod r less than epsilon, that means b minus ax is less than epsilon. We are looking into this criteria. So, it might give, if it converges, it will give us right, it shows that it will take us a x is equal to b location, but it can take a very high number of iterations if the matrix is not symmetric positive definite. So, this, if I have a symmetric positive definite matrix, this is the algorithm through which we will see later like Gauss-Seidel how, or SOR, how a computer program can be developed, and we can also demonstrate that the number of iterations and as well as computational time is much small than Gauss-Seidel or Jacobi or SOR method for a symmetric positive definite matrix. So, we will see in later class that how we can develop a computer program using this. And interestingly, this has only one matrix vector multiplication. Earlier we had two matrix vector multiplication. So, one has been reduced, there is only one matrix vector multiplication here. Now, we need to look into the convergence of this method. That is, for 2D I can give you some visualization that iteratively if we change the search direction, we should approach to the J minima, or this method should converge. Now, there are certain theorems and analysis which can show that the error, convergence means the error will be smaller, x minus x star is smaller than is the error x k minus x star. This error will finally reduce to a very small number given certain conditions. That let A be, the theorem for convergence tells that let A be an SPD matrix, that is a symmetric positive definite matrix, then the A norm of the error vector, which is x k minus x star is the exact solution of x is equal to b. Generated by steepest descent algorithm satisfy the relation mod dk plus 1 A norm of any vector is defined as E transpose A. So, dk plus 1 transpose dk plus this is basically d I am sorry, there is an issue. Dk plus 1 transpose A norm of dk plus 1, or let us take dk, its A norm is basically given as dk transpose A dk. This norm is satisfy the relation is less than equal to lambda max minus lambda mean divided by lambda max plus lambda mean of dk. So, if we have any initial, always dk plus 1 is less than dk. The error x k minus x star at any iteration is always less than the error in the previous iteration. Therefore, it should converge to a, finally this error should be a small value and it should converge to a small number, should converge to the right solution. However, the rate of convergence here depends on not on the spectral radius, rather the maximum and minimum lambda. So, the relation, the difference of the maximum eigenvalue and minimum eigenvalue of this lambda max and lambda mean are, there is no iteration matrix, are the eigenvalues of the matrix A only. So, it depends on the eigenvalues of the matrix A. So, this algorithm, and this shows that this algorithm will converge for any guess value x 0, because this is always a number less than 1. Therefore, dk plus 1 is always, error is always reducing. So, finally, the error should go down, it will start with some value, it will keep on, the magnitude modulus of error is always reducing. So, it will be a small number, and this is a positive number, right, because A is SPD, this is always greater than 0 as A is SPD. So, this number will be greater than 0 and reducing, that means that if this is dk A and this is k, this will asymptotically approach 0. It will never be exactly 0, it will be always greater than 0, but it will be a very small number and then it will be finally 0. So, this algorithm will converge for any initial guess x 0. This is a mistake here, this should be dk. I should correct it in the original notes also. This is dk. So, you can see dk plus 1 A norm is lambda max minus lambda mean of by lambda max plus lambda mean of dk, which is lambda max by lambda mean minus 1 by lambda max plus lambda mean plus 1 of dk. And spectral condition number, we have defined it earlier. Of any matrix is the ratio of lambda max and lambda mean. We have said that as small as the condition number, therefore, lambda max and lambda means are closer, it is easier, good for matrix solver. So, we are also seeing here, and this is always greater than, So, basically this is absolute, all these are absolute values. So, this is always greater than 1, all this should be in absolute value. So, this is always greater than equal to 1. So, as this value is close to 1, this number is smaller, is 1.000, it is a very small number. So, in very few steps the decay plus 1, the error should approach 0. So, if convergence spectral radius is, the convergence rate depends on the spectral condition number, spectral condition number low, spectral condition number that means faster convergence. And when discussing about condition number, we have discussed that if the condition number is small, then the convergence is faster. If lambda max and lambda mean are closer, the condition number are small, convergence is faster, and we can see if this number is smaller, we will reach the convergence faster. So, low condition number will give a faster convergence here. So, this is the first time we earlier discussed about condition number. We are seeing one example of condition number in first in the rate of convergence of the one particular matrix solver, which is the steepest descent method matrix solver. Okay. So, this method will converge, that means we started with some geometric functional, and we can see that once we have derived the algorithm, this algorithm converge starting with any guess value x 0, this algorithm should take us to the converged solution of Ax is equal to b, and that is only for symmetric positive definite matrix. Now, the question is that the entire exercise is only devoted for symmetric positive definite matrix. A matrix may not be symmetric. In reality, we deal with number of cases where we get asymmetric matrices. For example, if we think of a finite difference equation that we are discussing earlier, and if we use non-uniform grid spacing, the matrix will be asymmetric. So, how can we modify this equation for an asymmetric matrix? As well as in a general case, there can be a negative definite matrix. For positive definite matrix, there is a solution. If the matrix is not positive definite, if there is a negative eigenvalue, how to solve this matrix? This method does not cover those matrices, therefore, it is still now restricted only to a closed class of method, a small class of method, which is symmetric positive definite. Now, our next goal will be if we can extend this method for general matrices which are not symmetric and non-positive definite matrix, and what we will discuss for that is called a general projection methods. Instead of having a method for searching gradient through gradient search approaching the minimum value of a functional, we will see a more generalized method where probably the functional is little different. We are trying to find out minima of some other function, but solving a matrix which is not symmetric or which may not be positive definite also. Extension of this method will take us to general projection methods, which can solve a larger class of matrices. We will see that in the next classes. Thank you.